Okay, good. So last time we talked about binomial distribution, and we defined binomial distribution. We also came or discussed the assumptions which we make. That is when working with what? When working with binomial distribution. And I know you can remember that the major assumption which we made is that for the binomial distribution. Okay, each trio is what? Is mutually exclusive to each other, meaning it is totally independent. Like occurrence of one, maybe or the outcome of one trial, okay, does not affect the outcome of the what? Of the following trial. That's what we meant by mutually exclusive, that is assumption. So we also discussed about that is the mean and the variance for that is for the binomial distribution, where we said mean for that is for binomial distribution, we said it is n multiplied by p, whereby n is what? Is the total number of trials, and p is the probability of a success. Okay, we also talked about x as the that is of the what? The number of successful trials, and we talked also about q, whereby we said q, it is the probability of what? Of failure. Okay, and q, it's always equal to 1 minus what? P. That is 1 minus the probability of what? Of success. All right, that's number one. The other one we talked about, this was mean. We talked about that is variance, and for variance we said it is given by n p what? Q. This was the formula for what? For variance, and this can be even rewritten as np, okay, multiplied by 1 minus what? 1 minus p. This is what? This is variance. And of course, the standard deviation will be now the square root of what? The square root of variance. Good. That was about binomial distribution. We also did that is a formula for binomial distribution. And the formula, let me just clean this. And the formula was that, okay, that is n, it was n combined x, okay, multiply by, okay, multiply by, it was p raised to x, okay, multiply by q raised to n minus what? Minus x. This was what? This was the formula for binomial distribution. Okay, whereas we said that combination we can break it into n divide by that is n factorial divide by that is x factorial multiply by n minus what? X factorial. This is the formula for what? For that is combination. Okay, if we break it down to this, but we still have that is an Excel function which can what? Can give you the result of this even without doing it manually. Okay, and then we also said with this, of course, we can always rewrite this. We can always that is rewrite that as 1 minus p. Meaning if you only have the value of p, then it is easy for us to find the value of what? To find the value of q. Okay? Yes, that was the formula. Then let's now go to Bernoulli. Take note of this, because now Bernoulli distribution, it is a special case distribution of what? Of that is of binomial distribution, where n is equals to what? To 1. When is n is equal to 1, or if we when we make only one that is trial and then finish our experiment, then that will be what? That will be termed as binary experiment. Okay, but if maybe we have more than one trials, now we are talking about binomial distribution. Okay, so when binomial distribution, or in binomial distribution, when n is equals to 1, then we obtain what? We obtain the binary distribution. Okay, let's check on this. So binomial distribution is the sum of series of multiple independent and identically distributed that is Bernoulli principles. Okay, so it is like the sum of series of this. Like for example, if we have that is n is equals to what? To 2. It's like we are having when that is a formula when n is what? When n is 1 plus, and the same formula when n is what? When n is it's also 1. So making it 2. So with that, that's why we are saying binomial distribution is the sum of a series of multiple independent and identically distributed binary that is trials, that is IID, independent and identically distributed. Okay, so in binary, the experiment is said to be random and can only have two possible outcomes, either a success or a failure. For instance, flipping a coin is considered to be what? A binary trial. That is, flipping a coin once. I think they forgot to say that. Once. Meaning we only have one trial. N is what? N is 1. So flipping a coin once, we can say it is a binary trial. Why? Because each trial can only take one of the what? Of the two values, either heads or tails. Each success has the same probability. That is, the probability of flipping a head is 50, and also the probability of flipping a coin, that is a tail, it's what? It's also 50. Okay, so it is 50-50. And the results of one trial, okay, results of one trial does not influence the results of the other. So meaning now this is when we talk about that mutual exclusivity as what? As an assumption. Okay, so this is the major assumption we usually keep in this distribution. Okay, then for binary distribution, we are saying that it is a special case of binomial distribution where the number of trials, that is n, is equals to what? To 1. So when n is equals to 1, then we have what? We have binary that is distribution. And then the formula for binary distribution will be like Cx. Why? Since n is 1, no need to put 1 here. Then multiply by p raised to x. Okay, multiply by q 1 minus what? Raised to 1 minus x. So this is the formula for what? For binary that is distribution. Okay, yes. Any question on that? Any question on binomial distribution and binary distribution? Okay, good. Now let's continue with that is our last distribution, that is Poisson distribution. And Poisson distribution or is also it is also account distribution, or it's also known as account distribution. Okay. Yes, and here we will be talking about that is a probability, okay, that will show us the likelihood of or how many maybe an event that is will occur within what a period of time. Like for example, if we are doing an oscillation, when we are doing the oscillation, okay, we can take now that is oscillation as an example. Like we want to know, okay, how many complete revolutions are they called complete uh, uh, just a minute. So you can, that is you can discuss, okay, or sorry, not discuss. So you can come up with this example like that is oscillation, or you can count how many complete oscillations, okay, how many complete oscillations do we have between what, maybe within 2 minutes, that is when you start the oscillations, you can record how many oscillation will I get within that is 2 minutes, how many oscillation will I get within that is 3 minutes, how many oscillation maybe I will get within what, within 1 minute. So you can see here we have the aspect of what, the aspect of time. Okay. Okay, good. Now I want us to dig into that is the distribution itself. Okay, so Poisson distribution. So in Poisson distribution or Poisson distribution, it's a probability distribution, okay, that is used to show how many times an event is likely to what, to occur. Okay, a Poisson distribution, it's probability distribution that is used to show how many times an event is likely to occur over a specified period. Take note of that. How many times, okay, an event is likely to occur over a specified what, time period. Okay, so in other words, it is a count distribution. Yes, and this count distribution makes it to be what, makes it to be that is a discrete distribution, because when we are talking about count we are talking about discrete. Okay, so Poisson is one of what, one of the that is a discrete distribution. All right, good. Let's continue. So uh, Poisson distribution are often used to understand the independent events that occur at a constant rate within a given time period, and this distribution was named after that is French mathematician. Okay, it was named after French mathematician Simeon Denis Poisson. Okay, Simeon Denis Poisson. So the Poisson distribution, of course, I have talked about this. It is a discrete function, meaning that the variable can only take specific values, potentially infinite list. Okay, it can take a 0, it can take a 1, it can take a 2, it can take a 3, up to 5. Okay, or even more. Not particularly, it is limited to what? To 5. Okay, yes, but it does not take what? Decimals. It takes the what? The that is the space, or that is the whole values. So To put it differently, okay, the variable cannot take all values in any continuous what range. Of course, it can't take what decimals. Okay. Of course, at some point when we want now the probabilities, okay, when we want now the probabilities, we can get that is decimals. Why? Like for example, if maybe we want the probability that 20 events, okay, will happen within what? Within 5 minutes. So definitely that can be what? That can be computed as what? As a decimal. But here, the number of events which we are talking of, they don't take what? They don't take that is decimals. Yeah, I think we shall define this well when we will be doing that is the practicals tomorrow. Okay, so I will share the data set for that maybe after the class. Now let's go maybe and do some takeaways. So a Poisson distribution, and that is it's named after a French mathematician. Okay, and we've said it is used to estimate. You can take this. Kindly note this. It can be used, that is to estimate how many times an event is likely to what? Is likely to happen. Okay? Yes. Or it's likely to happen within what? Within a specified time period. All right. So now let's go to the second point. Poisson distribution are used when the variable of interest is what? Is a discrete count variable. Okay? Yes, Poisson distribution are used when the variable of interest is what? Is discrete variable. Many economic and financial data appear as count variables, such as how many times a person becomes unemployed in a given year, because of course this is number of events, because the event here it's unemployment. Okay, then we need what? The time. The time now it's the year. Okay, so with that we can do what? We can get to model like how many times a person become that is unemployed in what? In a given year. And with us and with this we can determine now when we do now the that is the cumulative or the density mass function, or the density mass probabilities, okay, for that. So the point or the event which has the highest probability, then it will mean what? It will mean that that is those are that is the time, or the number of times, or the number of events that maybe can happen within a specified period of time. Uh, so understanding distribution, that is Poisson distribution. Let's take maybe an example. Okay, let's take this is an example of how maybe we can that is we can use a Poisson distribution. Okay, very simple and to the point. Okay, so a Poisson distribution can be used to estimate how likely it is that something will happen, okay, that is x number of times. Like how many that is the probability or the likelihood of maybe an event happening more than what? More than maybe n times. Okay, so like for example, let's assume you have that is a cheeseburger that is fast food outlet or chain. Okay, let's assume you have an outlet. Okay, or like we have a Pizza Inn, we have Chicken Inn. Okay, yes. So let's assume we have a Burger Inn. Okay, or a burger outlet. So with that, um, on Fridays you usually get, let's say, two what? You usually get 200 what? 200 uh, customers every Friday. According to maybe historical data, you usually get roughly or an estimate of 200 people coming to do what? To buy your burger. So, what are some of the questions that maybe Poisson distribution can answer us, depending on that? That is depending on that data. So we have one question which we can answer using Poisson distribution. We can now do that, or we can now get the probability that more than the 200 people or more than 300 people will come to buy that is burgers maybe next Friday. Okay, so maybe we are used that is we are used to 200. Okay, but maybe a certain day or a certain Friday we might have a campaign, an external factor. Okay, which can affect what? Which can affect your numbers. Okay, so in this case we will now use what? The Poisson distribution to determine the probability that we will get what? We'll get more than maybe so let's say we have now, this is the probability. So it will be the probability that x, in our case x here, it's the number of what? The number of events. Okay, that is x will be greater than what? Will be greater than 100, 300. So this will be our what? Our probability, or our that is the probability. Here now what we'll calculate is the probability. If it's true, maybe next week Friday we might get more than 300 what? 300 people. Now the value of the probability is the one which uh, will now tell you if that's true or that's not true. Okay, why? Depending with the value of the probability which you get. Okay, so at least Poisson distribution is used to measure the probability of what? Of that is of events. Okay, yes, it will give us the probability of the events. All right. Okay, good. Now, I want us now to that is let's finish maybe this example. Let me reread it. So, for example, if an average number of people who buy cheese from a fast chain, that is someone is calling. Just a minute. Okay. Okay, I'm back. So, what is the probability that more than okay, let me start here. So, for example, if the average number of people who buy cheeseburger from a fast food chain on a Friday night at a single uh, restaurant location is 200. This is maybe the normal number we are used to getting. So a Poisson distribution can answer questions such as what is the probability that more than 300 people will buy burgers. Then the application of Poisson distribution thereby will enable maybe now the manager to introduce an optimal scheduling system that would not work with maybe a normal distribution. So with this, the manager can strategize and see maybe if he can optimize maybe the system, or maybe increase the head count in terms of the cooks, so that we might meet what we might meet that demand. So one of the most historical practical that uses Poisson distribution is when estimating that is the number of soldiers that is cavalry, that is soldiers killed due to horse kicks. Okay, it's funny. It's funny, but though it is a good example. Okay. Also, we can use Poisson to model like how many number of accidents. Okay, that is or we can use to estimate and also get to know the frequency of maybe car crashes in a city, or number of what accidents which might occur within a period of time, depending on the available historical data. So modern examples include estimating the number of car crashes in city of a given size. In that is in psychology, the distribution can be used to calculate the probabilistic frequencies of different types of neurotransmitter secretion. Okay, and also maybe in a video store. Okay, or if a video store averaged that is or as a 400 customers every Friday night, what would have been the probability that will get more than 600 customers come in any given Friday night? So that this is the same examples, that is this for video is the same example to what? The same example to the one of the burgers. Okay. Yes. So we can be what? We can be able to calculate a probability. Okay. Of maybe certain event occurring. Okay. Certain event occurring given that is the historical data. Okay. Good. Let's go to the final stage on how maybe this Poisson distribution can be used to what can be used in finance. So the Poisson distribution is also commonly used to model financial count data, more so when we are dealing with what only count data, where the tally is small and is often zero. Like for example, in a finance, it can be used to model the number of trades that a typical investor will make in what? In a given day. Or in a bank, we can measure the number of withdrawals maybe you or someone else can do what can do or can or the that is the number of transaction one can do within what? Within 1 month. Okay, so with that we can be able to do what? To model maybe those transactions and be able to know roughly in a month, maybe I do what? I do 3 to 4 what? 3 to 4 transactions, bank transactions. Okay, or if you are that is a gambler, you are used to betting. So with your historical data, we can know, or we can even use to model that is your um, your gambling behavior, like the probability, or that is the number of gambles, or the number of bets you can place within within a day, or within a week, or even within what? A month. With that we'll be able to what? To model your gambling, or your betting what? Your betting behavior. Okay, so that's an example. Basically, under Poison, we are focusing on the number of events within what? Within a given period of time. Then after that, we can even also try to get the probability, given the historical data, that a certain number of events can take place within what? Within a given that is time period. Okay, yes, it's like also in the what? In the, like, even this Shakaola thing. Okay, like for example, we know that is within maybe 5 days, or within 20 days, they were able to exhume what? They were able to exhume maybe 50 people. Okay, so we want to know, or we can model that maybe tomorrow they can what? All the possibility of tomorrow exhuming more by 2 times, or less, okay, the number which they usually exhume on daily basis. As well, we can also get a probability that maybe in the next week, or in next week, the number will increase, that is in tally, up to maybe 300. Okay, so with that, since we are talking about number of events here within time period. Remember, when I talk about next week, or that is, I talk about maybe next month, that is period. Okay, that is the period, and then we can be able now to count. That is, or use exhumation as what? As the number of events. Like in every that is exhume they do, they get this certain number of what? Of dead people. Okay, so with that you can as well that is use Poisson distribution to model that, provided we are dealing with events in terms of count, and also time, that is time period, as the definition of Poisson. The other thing, it is now that is okay, yeah. So as one example, in finance, it can be used to model what? The number of trends that a typical investor will make in a given what? In a given day, which can be zero, of course, which can be one, or it can be what? It can be two. As another example, this model can be used to predict what? The number of shocks to the market that will occur in a given period of time. Like it can be that is, it can be able to, shocks here might depend, or might mean external factors, which maybe will affect maybe a stock market. Okay, so we might be able to predict, that is, how many times maybe Safaricom shares will go down in what? In a year. Okay. Yes, we can measure that. So basically, that's all about Poisson distribution. Maybe what I can show you, it is the formula. So let's assume we have we need that is probability function. This is the probability function for that is what do we call it, by for Poisson distribution. So that is probability of event x occurring within what, a period of t time. So it is like probability of event x occurring within what, t time, will be equal to, okay, lambda, where lambda it's a constant, raised to what, raised to t. Okay, or we can say lambda, it is raised to the number of events, sorry. Lambda is raised to the number of events, that is x, okay, multiply by exponent of the lambda. Lambda is a constant here, okay. Then divide by what? Factorial of what? Of x. Whereby x is what? Is the number of events occurring, okay. Just a minute, just a minute. Yes, x is the number of events occurring and lambda is a constant. Okay, and when we do a mean, or when we compute the expectation of x using Poisson distribution, we usually get lambda as what? As our mean. Okay, so in this case, this lambda, which is the constant, it's also what? Sorry, here should be a negative. Sorry for that. It is exponent of negative lambda. So the mean for Poisson distribution, if you do the expectation, then the mean for that is for Poisson distribution is what? Is that is its lambda. And Poisson distribution, it's the only distribution where mean is equal to what? To variance. Okay, meaning now the variance of Poisson distribution is also lambda. You can go and confirm that, so that I might not be but that is by I might not be wrong, but this is what that is I learned. Okay, that is, Poisson is the only distribution where the mean is equal to what? It's equal to variance. Okay. Yes. Yes, there is someone with question. So before maybe you can ask, that's all about that is the Poisson distribution. Then now tomorrow we shall now do the practicals for normal distribution, for binomial distribution, and for Poisson distribution. Since Bernoulli distribution, it's the same as binomial distribution when n is equals to what? When n is equals to 1. Yes, so